Now we go to the inverse of a matrix using the adjoint. Note that the adjoint of a given square matrix is the transpose of the matrix of cofactors. So the first thing you need to do when given a matrix, find the minus. From the minus, you get cofactors using the formula minus 1 to the power I plus j times mij for the corresponding cofactors to particular minus, and then formulate the matrix of cofactors, and then thereafter find the adjoint. Note that again, the adjoint is the transpose of the matrix of cofactors. So here I've given an example of a matrix A, and we found the matrix of cofactors, and therefore the adjoint is the transpose of that matrix. And then also we ought to recall the formula for the inverse of a matrix, which is 1 over the determinant of A multiplied by the adjoint. So for the given matrix A, if we were asked to find the inverse of that matrix using the adjoint, then we would use that formula and then substitute the adjoint of A in, calculate the determinant of A, which is 14. Therefore, the inverse is given by this matrix, where you multiply 1 over 14 to each and every entry in the adjoint. So some exercises where you need to find the adjoint of a given matrix. So remember, we have to first find the minus and then find the corresponding cofactors and then formulate the matrix of cofactors, and then the adjoint will be the transpose of that matrix of cofactors. So try it out for each of those two matrices, and then thereafter find the inverse, which is 1 over the determinant of A multiplied by the adjoint of A, and that means for number 2 it will be 1 over the determinant of B multiplied by the adjoint of B. Now we are asked to make use of the Gauss-Jordan elimination to find the inverse of the coefficient matrix and then thereafter solve the given system. Note that for the Gauss-Jordan elimination, the coefficient matrix is augmented to an identity matrix, and then thereafter do row operations such that the coefficient matrix is an identity matrix, and then the inverse matrix will replace the identity matrix that is on the right hand side. So for this particular system, first things first, we have to make sure that we write the system in matrix form, do the augmentation of the coefficient matrix A with the identity matrix, and then do row operations. So the first thing, we need to change the 2 to a 1. So therefore we divide the whole row by 2 and substitute in row 1. And then thereafter use row 1 to eliminate 3 and 2 below it. So for row 2, it will be minus 3 row 1 plus row 2, substitute in row 2. For row 3, it will be negative row 2 times row 1 plus row 3, substitute in row 3. Please check the steps and see whether you'll get the same answers. So here are the steps. We said half row 1, substitute in row 1, and then -3 row 1 plus row 2, substitute in row 2, and -2 row 1 plus row 3, substitute in row 3. Please check whether the entries are correct. And then thereafter we noticed that the entry -3/2 and 3/2 can cancel each other out if we add them up. Remember, identity matrix requires the first row to be 1, 0, 0. So that means even -half as the third entry in the second row and half in the first row can be added up so that we produce a 0 in the first row, third entry. So what we need to do then is to add those two rows and substitute into row 1. So we say row 2 plus row 1, substitute in row 1, and thereafter make sure that the first non-zero entry in row 2 is 1, requiring that we multiply the second row by -2/3, producing that row. Then we notice that also below 1 in the second column, we need a 0. So what we do is to interchange row 2 and row 3, because already row 3 has 0, 1, 0, which is supposed to be in row 2, so that we have that augmented matrix there. And then thereafter use now our new row 2 to eliminate 1 in the third row. So that means it's negative row 2 plus row 3, substitute in row 3, and then we end up with 1/3 as the only entry in the matrix A that needs to be changed to 1. So our inverse of A is the augmented matrix with -1, 1, 0 in the first row, -1, 0, 1, second row, and 6, -2, -3. And then to solve the system, remember we're supposed to solve for x, y, and z. We always multiply A inverse to the matrix of coefficients. So we substitute and then we get 2, -1, and -2. Please check the steps and see whether you're going to get the same answer. Some exercises. The first one, you are given a 4×4 matrix. Just calculate the minors and cofactor and the corresponding cofactors for that have been given to us. Remember, for a minor, you delete a row and a column. So M13 means you delete the first row and the third column. So you are left with a 3×3 matrix. And please check whether you are going to get a 0. I believe I got a 0. Just check whether you also will get a 0 for M13, meaning that C13 will be -1 to the power 1 plus 3 times 0. And check also what you would get for B and C. And then the next one, we are asked to use the Gauss-Jordan elimination to find the inverse of the coefficient matrix and then solve the system. So please go through the steps that we've already expounded on and then be able to use A and P. Remember, I'm hoping you're noticing the first row will be 0, 2, -1, augmented to 1, 0, 0. But then you cannot have 0 as the first entry. So it requires that you do an interchange of rows so that we can have a 1 as the first entry. Solve and see what you get. Now, we solve systems of linear equations directly. Note that for any system, it either falls into one of the three categories. It will have exactly one solution, infinite number of solutions, or no solution at all. So it means that when we have one solution and an infinite number of solutions, we call it the system a consistent system of linear equations. But if it has no solution, then we say it is inconsistent. Now let's make an illustration. I've given you a general system of two linear equations with two unknowns. Graphically, if those two equations represent equations of straight lines, and when you draw them, they give you two parallel lines, line 1 and line 2, then it means you have a situation where there is no solution. Remember, in order for you to have a solution, you must have a point of intersection. Then the second graph gives us one solution because there is only one point of intersection between the two lines. But then for infinitely many solutions, if you get line 1 and line 2 being represented by the same equation, when you draw it on one straight line. Then that means the points of intersection between the two lines are many. That is why it has got infinitely many solutions. The example for the third one, if for instance you have x plus y equal to 1 and the second equation is 2x plus 2y equal to 2. So that means one equation is a scalar multiple of the other equation. So if you multiply the first equation by 2, you'll get the second equation. Or if you divide the second equation, you get the first equation. So you end up with one equation all in all. Then it means both lines are represented by the same equation, so you draw them on the same line. Now I would like you to solve the following systems and sketch each system as a pair of straight lines. And you see what you're going to get, whether you're going to get one solution, infinitely many solutions, or no solution whatsoever. Now, one other thing that is worth noting is that for an inconsistent system, inconsistent, it means no solution. When you do row operations and you reduce the equations, we end up in the last row. That is the third equation, which is last row when using matrices with 0 equal to a number. For that particular system, we got 0 equal to -2. And therefore, it is not possible for you to solve for z because the last equation, 0 can never be equal to a number. Therefore, we say the system has no solution. So you reduce or you solve the system until you get a 0 equated to a number. Even if it's a 2 by 2 system, you can get such a situation. Infinitely many solutions. When you've done row operations, the third row or third equation, when you're using simultaneous equation, will give you 0 equal to 0. Note that once you get the third equation is 0 equal to 0, now you are left with two equations with three unknowns. So that means you have to let the last variable be equal to t, and which implies that t can take an infinite number of values. You can substitute anything. The values of x and y will change depending on the value that you've given to z. So there is no one solution when you get 0 equal to 0 for a 3 by 3 system, because you'll end up with two equations with three unknowns, being forced to let the third variable be equal to another variable, which is t, which can take any value. Now, among these exercises that we have here, what you are asked to find is the value of k. And the value of k, that will give the system exactly one solution for A. That means they must have a point of intersection. And then infinite number of solutions. That means if the first equation, when you multiply it by a particular constant, will give you the second equation, find that value that will make sure that the second equation reduces and be exactly like the first equation. No solution. It means when you've reduced this equation, you get 0 equal to a number. You can be able to determine that as well. Then the application of determinants is used in what we call the Cramer's rule. Cramer requires the use of determinants to solve for the variables. So first things first, you need to have a system of equations. It could be two equations with two unknowns, or three equations with three unknowns. Write the given system in matrix form. Then let's see how then you use the determinants to solve for the variables x1, x2, and x3. Note that b1, b2, b3 are the constants. So x1, x2, and x3 will be divided by the determinant of the coefficient matrix. Matrix A, determinant of matrix A, determinant of matrix A for all three variables, but the numerator changes in the sense that for the first variable, the first column of A is replaced by the constant. For the second variable, in A, you change the second column and replace it with constants. And for x3, we change the last column and replace it with the constants. And then we solve for those determinants. Once again, the first variable, its numerator will be the determinant of a matrix represented by the constants replacing the first column of A. The second variable will be the determinant of a matrix where you've replaced the second column with constants, and the third variable is the determinant in that numerator of A, where the last column has been replaced by the constants. Let's do some examples using Cramer's rule. We are given the system 4x minus 2y equal to 10 and 3x minus 5y equal to 11. Then we formulate the matrix format, and then the variables we have to solve is x and y. Remember that both x and y have got the same denominator. That means the determinant of the original A, that is coefficient matrix, but the numerators change. The numerator for x is the determinant of a matrix where the first column of A is replaced by the constant matrix. So you've got 10 and 11, and the last column of A remains the same. But for Y, the determinant of that numerator is the determinant of a matrix where the second column of A has been replaced by the constant matrix. And then you enumerate. Please check whether you'll get 2 and -1 as values for X and Y. So Cramer's rule can be used on a 2x2 system as well as a 3x3 system. Number 2, we have now a 3x3 system. First things first, change to matrix form, and then thereafter, note that the determinant of A is on all three variables in the denominator. The only change we find is in the numerator. So again, first variable, remember the constant matrix goes into the first column. So I have here 1, 0, and 2. Then all the others will go in. But for Y, that 1, 0, 2 goes in the second column. And then for Z, that constant matrix go to the third column, 1, 0, 2. Note that you just replaced in A one column, so that means all the other columns remain the same. And then you fill in all the answers, and then you find the determinants, find the values of those determinants, simplify, and get the values of X, Y, and Z. If you know how to evaluate the determinants, then it's easy to get to use Cramer's rule to solve a system. Note that when you're given questions, the instruction will be clear. Use Cramer's rule to solve. So for now, we've learned on how to use the Gaussian elimination to solve a system. We've learned on how to draw the graph so we can solve it graphically. We also know how to use the inverse method, and we also know how to find the inverse of a 2x2 and the inverse of a 3x3 matrix using the adjoint of a matrix, as well as using the Gauss-Jordan elimination. Also, we know how to solve a system of equation directly using the Gauss-Jordan elimination without calculating the inverse. And now lastly, we have used the Cramer's. Here are some exercises that we ought to do. Now note that the constant matrix has got variables x and y. So here we are solving for x prime and y prime. That is why it says solve the systems in terms of x and y. So x prime might have x and y prime might have x and y, depending on how your calculations go. So in both number 1 and number 2, we don't have constants. Instead of constants, we have variables. So here you may use Cramer's rule. You may use the inverse method. You may use the Gauss-Jordan elimination, or you may use the Gaussian elimination. That depends on you, which method you see suitable or easier to use, because the instruction does not specify which method, just simply say solve. So you use what is more comfortable to you.